Okay, so good evening. Are you able to hear me?
Yes, sir, we can hear you. Good evening.
Okay. Alright, so we'll start from where we left off last on Monday. Right? So Monday was when we last met. So okay, so we'll get started. So what were we discussing last time? We were, I think, just about to start discussing the
Feature
kernel
transform.
PCA. Sorry.
Sir, kernel.
Feature transformation, I think.
Yeah. So we had just about discussed the feature transformation, and we were starting with this kernel PCA algorithm, right? So describing the kernel PCA algorithm. So what we'll do is we'll go ahead and complete the description, and then we look at some demos of what it looks like. Okay.
Sir, when we are expecting to look for like some doubts if we are having?
In which week?
Week 2 only. Week 2.3. So I think will we be able to connect after the class, like at the end of the session? If
Yeah, we'll try to do that at the end.
Okay.
Okay. So yeah. So we had this problem with standard PCA, which is that there are two problems. One is the computational cost is quite high when the number of features are high, right? So sorry, when D is much greater than N, you have an issue with doing standard PCA, and that will take time. And the second is if you have non-linearity in your data set, then that's also an issue, right? So if you have non-linearity, then there's a problem. So what kernel PCA allows us to do is to overcome both these problems with a single approach, right? So towards this end, what we did was we looked at the idea of a general nonlinear transformation, right? So it takes RD, so your data points are in RD, and it takes them from RD to some R capital D. So the typical one that we looked at was phi of, so we looked at this example of 2D, right? So you have x1, x2, then polynomial transformation will look something like this. So 1x1, x2, x1 square, x2 square, and x1, x2, right? So this is an example of a polynomial transformation, and the idea is if you move to a higher dimensional space,
Call it a quadratic kernel.
it is not a kernel, right? It's a transformation.
Okay, then why means can we call it a quadratic transformation?
I just called it that, right? I call it a polynomial transformation, which is a much wider class of transformations. Quadratic is a specific instance of that.
Okay.
Okay, so you have this transformation, and the idea is the transformation helps you in linearizing the data set in some higher dimensional space, right? So that's the whole idea. Now, the way this phi is what happens is typically phi is not explicitly given to us. So, and computing phi for every data point is going to be a really hard task, right? Because that will again blow things up. So another formula that I mentioned last time, right? So this is, if you have P as your polynomial's degree, and if you have D features, then these are the number of features of your transform space. Okay. So if you have something like, say, 100 features to begin with, and if you are, even if you're doing only a degree 2 transform, this will be 100 choose 2, and this is roughly 10,000. Okay. So you'll have to deal with a covariance matrix of dimension 10,000 cross 10,000. So that's huge. Okay. So explicitly computing phi of x is not really a good idea. So the idea of a kernel is to help us in this regard, right? So what the kernel function does is, so if you have kernel function, first of all,
Sorry,
from
sir,
R,
here
D,
D is the features or it's the degree?
T is the always the number of features.
That is 100, right? You said.
Yeah.
That you
Yeah. So
put,
yeah, this is both are the same, right? So 102 choose 2 and 102 choose 100 are the same. So
okay.
yeah, right. So you have a kernel. The kernel is a function that accepts two data points as input, and it's going to return a scalar value. Okay. So a typical kernel that we study in this course is called a quadratic, the polynomial kernel. So it could be a quadratic kernel, it could be a cubic kernel. So the general formula is you have x comma y, x and y are vectors, and then you do x transpose y plus 1, and you raise it to some power, right? So some power p. So this is a polynomial kernel of degree p, right? So this is how it looks like. So this is how it looks. And specifically, let's take the case of this x transpose y plus 1 whole square, right? This is the quadratic kernel. Now, what the kernel does is it calculates this dot product, right? So phi of x transpose phi of y for some suitable phi. Okay, so we don't actually explicitly define what phi is. We allow the inner product or the dot product computation in the transform space to happen via the kernel. Okay, so let me write it down. So the computation of the dot product between data points in the transform space, right? When I say transform space, I mean this larger space that we are going to is achieved via the kernel. Okay, so the kernel is what allows us to take the dot product between the data points. So these are data points in the transform space, and that dot product is calculated using this kernel. So the nice part about this is that you don't need to explicitly compute phi. Okay, so this dot product is implicitly computed using the kernel k. Okay, so this is the whole idea of kernels. So kernels allow you to kind of go to a higher dimensional space and compute dot products there without actually doing it. Okay, meaning without actually explicitly doing it. Right. So is this?
Sir,
Yeah.
are we expanding this x transpose y plus 1 whole square in the next step?
That is not needed, but yeah, if you, that's what the prof has done in the lectures so as to demonstrate that this actually corresponds to some phi of x transpose phi of y.
And this phi is the kernel function.
No, the phi is the transformation. The kernel function is k.
Okay. So we are doing okay.
Okay, so the reason why we use a kernel is because when we describe the PCA algorithm, you will notice that everything is actually about dot products between data points. Okay, so that is why we make use of the kernel. So I hope by now all of you have seen the lecture, so I'm not going to stress this point too much. So we can, I think, directly go to the algorithm, describe it, and then if we have any questions, we can come back. Okay. So the first step is say you fix some kernel k. Okay, you choose a kernel k, and then you compute the kernel matrix or the gram matrix, which is sometimes called the gram matrix, where it is nothing but given by capital K, and it's a n cross n matrix. So let me first write that down. It's an n cross n matrix, and the ijth element, right? Ith row, jth column. That element is nothing but the kernel evaluated on the data points xi and xj. Okay, so you have to just evaluate this. For example, if it's a quadratic kernel like this, you'll have to take the dot product of the two data points and then add 1 to it and square it. Okay, so this will be an n cross n matrix. And once you get the matrix, so this is the algorithm. Kernel PCA, right? So once you get the matrix, what do? You compute the eigenvectors and eigenvalues of k. Okay, so remember that these are going to be, let's call them v1 comma dot v small r. So that is these are the eigenvectors, and the corresponding eigenvalues are lambda1 dot lambda r. These are the eigenvalues, and these two conditions you must know, right? So the eigenvalues are increasing, right? Decreasing order. So this is greater than or equal to lambda r, right? And these are all greater than 0. So some of them may be 0, but then I am choosing r in such a way that these are all non-zero eigenvalues. Okay, so these are all non-zero eigenvalues of the kernel matrix. Okay, these are the eigenvalues. The eigenvectors are, in this case, unit norm. Okay, whatever you get, you assume that it is unit norm. Whatever the black box does to your kernel matrix, that is going to return unit norm eigenvectors. Okay, these are the first three steps. So fix the kernel, compute the kernel matrix, and then get hold of the eigenvectors and eigenvalues. And you're still talking about this matrix phi of x transpose phi of x, right? So it's good to keep in the back of your mind that k is actually, for some phi, it is actually phi of x transpose phi of x, right? So you now need to get back to phi of x transpose, right? That is the covariance matrix. So recall that this is what we mean by the kernel matrix, and also recall that this is what we mean by the covariance matrix, right? So we want phi of x transpose 1 over n, right? So this is what we are interested in. These are the eigenvectors of this matrix is what we want, but we start with this. Okay, so once you do this, you need
C is that covariance matrix, right? And here, whatever we get will be eigenvalues, right? For the diagonal matrix.
no, you will get both eigenvectors and eigenvalues of the kernel matrix.
So whatever we are doing is on kernel matrix itself.
Yeah, you only work with the kernel matrix and not the covariance matrix. So that is.
Can you scroll a little bit up? Okay, we are doing okay.
Sir,
Yeah.
In the books, I found that the kernel, this is a covariance matrix. Here, n is replaced by n minus 1. It is divided by n minus 1. Which one is the correct? Division by n is okay, or division by n minus 1 is okay?
Okay, you can use n for now. So there are like, that is the unbiased, there are biased and unbiased estimates of your covariance matrix. So the unbiased one, I believe, will you use n minus 1, right? You would have read this in stats too, right? So the unbiased estimate of the covariance matrix is 1 by n minus 1 phi of x transpose. But you can use this. It's not, as far as our course is concerned, it's not going to cause too much of problem. So 1 by n is fine.
Okay, right. Thank you.
Okay, so
Right, sir.
yeah. So till this step, I hope it's clear to everyone, right? So this is all, we are just following a sequence of steps, and this part we'll never ask you to do in the exam. This is assumed to be given to you, right? So you'll be given the eigenvectors and eigenvalues, or maybe one of them. So you will never be asked to compute the eigenvalues given a matrix, because it's proper MLF, so we don't go there. So once you have V1 to VR, this is not there in the algorithm, this will be changed, but what you ideally need is, you need to go to the eigenvectors of C. So how do you go to the eigenvectors of C once you know that these are the eigenvectors of capital K? What is the formula for going from eigenvectors of K to eigenvectors of C? This, from here to here you have to go.
We should divide by under root and lambda, I think so.
Okay, only that. So eigenvectors of C, how do you find that? So do you just divide V1 by root lambda, or?
Root and lambda.
Yeah, okay. So I am assuming that the eigenvalues are lambda, and professor assumes that they are n lambda. Small difference, but still. So is it enough if you just divide this by n root lambda or root n lambda? Is that all?
No, sir. No, sir. Will it be also
Eigenvalues also changes in
eigenvector?
eigenvectors too.
So if you multiply by x.
Yeah. So you have to multiply by x, or in this case phi of x, right? So you have to multiply by phi of x since we are in the transform space, right? All this is happening in the transform space. So this is phi of x into v1 by root lambda, or if you are following the convention that SR has used, it is root n lambda, but I'll stick to root lambda here. So is this clear to everyone? We did this last.
Sir, this is for individual x, right?
This is an eigenvector corresponding to the eigenvalue lambda 1
Okay.
of the covariance matrix.
Mhm.
Is this clear to everyone, this part? Okay, I'm assuming it is.
Sir,
Yes.
how you will find that 5x?
Phi x, yeah, that's a good point. We can't find phi x, right? So I'll come to that. So this part, that's why I said that this is actually not there in the final description of the algorithm. So the second step is you don't know phi, okay? Because if you knew phi, even if you know phi, you already know that computing 10,000 features is meaningless. So you can't keep doing that for every data point, right? So you don't know phi, or rather you don't want to go there. So the only thing that is therefore possible is getting the projection of the data points onto the R principal components, right? So that you can do. So you can, these are the principal components, by the way. So these are eigenvectors of C are what? The principal components, right? So you have the R principal components, and you can project you can get the scalar projections, right? So what is the scalar projection of, let's say, the data point 1? So let's phi of x1 onto this first principal component. What is that going to be? If you want to project phi of x1 onto the first principal component, what will you do? So let's go back to standard PCA, right? So if you have a data point x and you want to project it onto the first principal component w1, what will you do?
Yeah, x transpose w into w.
X transpose W1.
Okay, so x transpose w1, right? So you want only the scalar projection. So we are only looking at scalar projection. So here, likewise, what will it be?
It is 5x
Transpose this quantity.
Yeah, just transpose this. That's all, right? So nothing hard. So same thing. We are not doing anything new here. We are just taking projection. So phi of x1 transpose phi of capital X v1 by root lambda 1. So there are too many symbols. That's the problem. But otherwise, we are only taking projection of the point v1, the data point x1 on the first piece. Okay, so what will be the, now how many components will this vector have?
Same.
First of all, will this be a vector or a scalar?
Scalar.
This is a scalar, right? So this quantity is a bit tricky to deal with. So notice that phi of x, so I'll just write down the dimensions of the matrices or the vectors involved. So phi of x is a vector, okay? That's going to be 1 cross d, okay? So it's like you are in the transform space. Now phi of capital X is a matrix, right? This is a matrix. So this is capital D cross n, okay? And v1 is an eigenvector of capital K, right? So what will be its dimension?
n cross 1.
N cross 1. Okay, so if you put all this together, if you multiply it, you will end up with 1 cross 1, right? So this is a scalar. So this is a scalar. That's why we are interested in the scalar projections, right? So what we have given here is the scalar projection of the data point phi of x1, okay, onto v1. Okay, this is onto the first PC.
Transformed one, right?
Yeah, transform. Yeah, in the transform space, right? So now, okay, so right, so this you have to know. Yeah.
So scalar projection is the means the modulus of the vector projection.
Not the modulus, right? It's just scalar value that goes behind the before
Because
the
the
vector.
okay,
So in
scalar value.
general, you say that this is the projection, right? So X transpose W W, where W is unit norm.
Correct.
So
Right.
this is the scalar
It's-
projection, X transpose
Right.
W.
Right. Okay. Okay. Right. Okay.
Okay, now let's look at this. This part deserves little more closer look, right? So how are we going to calculate this without knowing phi? Okay, so this is important to know. So notice that this is nothing but, I will write it down as phi of x1 transpose. This is a matrix, right? If you recall, this is phi of x1. This is a matrix of, this is your data matrix, but in the transform space. Okay, so this is your matrix in the transform space, and this is v1 by root lambda 1. I'm not changing that. Okay, so once again, I will write it down this way. So I'm just expanding this out so that this becomes a little more clearer. So I hope this is clear, right? So this is your data matrix, but in the transform setting. So it is capital D cross N, and this is your vector. Now, if you multiply the first two, so this is 1 cross B and B cross N. If you multiply this, what will you get? What object will you get? 1 cross
1 cross N.
1 cross N, right? So you'll get a vector, a row vector. So the row vector will look like this. So phi of x1 transpose phi of x1. And the second one will be phi of x1 transpose phi of x2, so on and so forth. The phi of x1 will stay constant, but the other member in the dot product will be one of the data points, right? So one of the n data points. Okay, so this is what is the first, what is this row vector actually? Is it the row of some matrix that you already know?
Covariance.
This one, right? The kernel matrix, right? This is nothing but the first row of the kernel matrix. So I'll call this K1. Okay, V1 by lambda 1, root lambda 1. So there's nothing but the first row of the kernel matrix. So what is the kernel matrix? In case you're wondering what it is, so let's assume that there are only 3 data points, right? So this is phi of x1 transpose phi of x1, right? And this is phi of, it's okay, it will take time, but still. So phi of x1 transpose phi of x2, and this is it's no copy paste. Okay, this is first row of the kernel matrix. If there are only 3 data points, so if there are only 3 data points, this is how the kernel matrix will look like, right? And it is a symmetric matrix, so I only need to fill in these, and then you can figure out what the others are. So this is second row will be the dot product of second data point with everything else. So second data point with everything else. Third row will be third data point with all the other data points, right? And this is this symmetric, therefore this will be the same as this for the sake of completeness. So this will be, and this will be 3 3 1 and 3 2. Okay, so this is the kernel matrix. This is how it will look like for 3 data points. Okay, so this is like 3 cross 3. In general, it will be n cross n. Okay, so that's what I have here. Phi of x1 transpose phi of x1, phi of x1 transpose phi of x3 or xn. Okay, so this is the first row.
Sir,
Yeah.
The matrix phi of capital X is the transformation applied across every column, right?
Yes, yeah. Every column of phi of capital X will be phi, the transformation applied on every data point. So
Okay, so
that
thank
is phi of capital X. Okay, so this is, remember this again is a scalar. Okay, so
Excuse me if I can hold you on.
yeah,
So
yeah.
there is a similar expression there in the lecture where the professor has mentioned as phi xj. Is the capital X similar to that?
Phi xj.
So it's like phi xi transpose wk, where wk is a vector, eigenvector, and then the same thing he has expanded wk, where I can find that the one which you have written phi x capital X v1 under root lambda 1. So that
Right.
capital
So
X is, yeah.
so I'm just doing exactly what Sir has done. Only thing is that I have used the notation will be a bit different. That's all. So in terms of, so so think about it this way, right? When you go back and you start preparing for this again, you have, so this part is, I hope this part is clear, right? The kernel,
Yeah,
computing the
yeah.
kernel matrix, that is standard. So
Mhm.
computing the eigen values, we are not very interested in here. So you can even forget that for now. The eigenvectors, right? So the difference between what I have used and what Sarah's used is it's here. So the prof says that the eigenvectors are n lambda 1, n lambda r, and I am saying that they are lambda 1, lambda r. Okay, just a change in the way we look at it, right? That's all. So
No,
that
I
is,
was just trying to look for analogy. If I'm getting the points correct, so instead of xj, we are having x over there, capital X over there in the last one, where you have mentioned
xj.
along. Uh,
No, if the prof has used xj, that would mean a data point, one data point. Capital X is the entire matrix, data matrix. Okay, so I think Sir has used alpha and beta, right? So if I'm not wrong, alpha,
yeah, alpha kj. Yeah.
yeah.
Yes, sir.
So alpha would be v, I guess, in this case, and beta would be alpha by root n lambda, right?
Yeah,
Uh,
yeah.
yeah. So that is the, so that's all I'm saying. So alpha, instead of alpha, I'm using v, and instead of beta, I'm not introducing beta. I'm just saying that it is v1 by root lambda. So I'm just sticking to that alpha itself.
Sir, lambda 1 and n lambda 1 will be different now, sir.
Yeah. So, but that is correct. But what we need to understand is we need to divide by the root of eigenvalue of the matrix K. That's all we need to do. Okay, so you can call it n lambda, you can call it lambda, but what matters is whatever eigenvalue you get, right, from the matrix K, kernel matrix, you have to divide by square root of that. That's all you need to remember.
Okay.
Okay, so you can call it n lambda or lambda. That doesn't matter. So the reason Sir has used n lambda is finally when you come to the eigenvalues of C, you can call them as lambda. Okay, so in fact, maybe if that is confusing, I can go back. It doesn't matter. So you can call them n lambda. Doesn't matter. So you have to just make sure that you divide by the eigenvalue of the covariance matrix. Sorry, the kernel matrix, square root of that. Okay. Yeah. So this matrix manipulation is a bit hard to process, digest. Okay, but it's not too hard. You just need to work on it a bit. So do you want me to continue doing this for one more? So that's actually a very nice formula at the end. So do you want me to go and derive the whole thing, or is it okay if I just give you that formula?
If it won't take much time.
Yeah, so it won't take much time. So, okay. See, this is what we have done. Are most of you with me, if not all of you, are most of you fine with how we obtain this?
Yes, sir.
Okay, so this is first row of k into v1 by root lambda 1. This is for what? This is for the scalar projection of the first data point onto v1. Okay, so if you want the scalar projection of phi of x1 onto vj in general, okay, not onto vj, onto the jth principal component. of the, what will it look like? It will be the same K1, right? You are still
Vj by root lambda.
yeah. So K1 Vj by root lambda
Lambda j.
j, right? Now I'll just change this to scalar projection of xi, right? Any data point. So if I change this from 1 to I, what will change here? This alone, right? The ith row. Instead of the first row, you need to take the ith row.
Sir, just a suggestion, like because Vj is a column vector and capital Ki is a row vector, unless you mention them explicitly, there might be some confusion, right? Because usually
Yeah. That is true. Yeah. So actually, what I have done in my notes is something slightly different. So let me see. So K, yeah, it's hard to explain this. So Ki, so maybe I'll just call it. Is it okay if I call it transpose? I hope you'll understand this is the first row and this is the ith row. Is that fine?
yes, sir.
Okay. So I hope this is fine, somewhat at least till this point. So these are the projections of. So you now know how to get the projection of any data point onto any principal component. Now, all that remains is putting these things together. Okay. So I'm going to make a big jump now. So bear with me. I'm going to add all these eigenvectors v1 to. So this is what? This is v1 by lambda 1, right? So and so on till vr by lambda r. Okay, there are these many eigenvectors. I'm adding all of them into a matrix and calling this matrix capital V. Okay, so all the eigenvectors are, so there are r eigenvectors, okay, of the kernel matrix K, right? So I'm adding them to the matrix V. So what is the dimension of V? Or shape of V is going to be what?
N cross R.
Yes, that's correct. N cross R. Okay. Now this is that. Now, if I multiply, so I'll use this same thing for now. Instead of calling it V, I'll come back to this in a minute. If I multiply K with this matrix, what will happen?
You'll get that phi thing. No, phi
Something
transpose.
that we saw before. So this is, I hope you all agree that this is, we did in first week, we did this different ways of multiplying matrices, right? So this is
No
one way
issue,
of
right?
multiplying matrices. Do you all agree that this equality holds?
Every element is multiplied with that, right? Like,
Capital K, yeah. So capital K multiplies every column of this matrix, and that, so capital K into this capital K is the matrix, right? N cross N. This is N cross 1. N cross 1, and you'll end up with an N cross 1 vector again.
so with this notation, we are meaning not individual elements, but the entire column is getting multiplied by this, right? So the columns are getting added, right?
Well, so okay. So what I mean is,
what we were doing, right? We were like multiply, but then individually we were multiplying the columns, and then we were adding them up, and we were saying that that is equivalent to actually multiplying the matrix and then getting the final one, right?
yeah, something like that is happening in each one of these columns. Okay, so see what I've done is, if you have okay, so if you have 1, 2, 3, 4, 5, 6, right, and if you have another matrix which is made up of these columns, okay, let's say there are 5 columns. So the way to look at it is multiply the matrix with each column. Okay, whatever is the result, that will be the first column in the output matrix, right? Corresponding column in the output matrix. So I'm calling this A, right? So I'm calling this A. So the first column of this matrix will be, output matrix will be A times V1. The matrix vector, column vector product, right? And it will be A times V5. So if you have a matrix, and if you have another matrix which is represented as a bunch of columns, this is what will happen. Do you all know
So you are
this?
multiplying entire matrix with a column.
Yeah. So think about it, right? So this is actually not very hard. So this is why we did that in the first week. Think about only one column instead of, let's say this is just one column vector. What will be the output?
Okay.
You're just multiplying a matrix and a column. AV1, right?
AV1.
So that is the first column. Now the second column in this if you go back to this generalization, the second column is nothing but A times V2.
Basically, my question is like, if A is a matrix and we are multiplying it by the column, then how we are getting that AV1 as a column? Means I get that we will get AV1 as column, but why column? How? Means we have two rows also there, right? For A, we will have two rows. So how?
Okay, so you can go and derive. So you can actually go and prove this, right? It's tedious algebra, but it's how do I put it? So how do you multiply a matrix and a vector?
Okay. So V1 is the vector and A is matrix. So we are multiplying the entire matrix with the column of that particular vector.
Yeah.
Either
So
it's a row vector or column vector.
Well, in this case, it's a column vector. If it's a row vector, it will be different. So I request, I know this is hard, but I request all of you to get used to these things, right? Because not just in machine learning techniques, if you go to large language models, deep learning, so deep learning is like the follow-up to this course in the degree level, right? You will see a lot of matrix multiplications and modern neural networks, right? What the ChatGPT, whatever you are seeing, they're all trained by an algorithm known as back propagation. Okay, so this is called this actually chain rule applied to, chain rule, right? All of you, the d by dx whatever, right? So that is chain rule, and there are multiple variables, right? So it's actually the chain rule with a lot of matrix multiplications in it. Okay, so matrix multiplication will not leave you with MLT. It will stay with you till the end of this program and even beyond. So there are only 4 ways of multiplying matrices. So I please request all of you to get used to them. Okay, so because if I start explaining how this works, then we'll kind of go away from the core subject we are trying to work on. Okay, so yeah, this is what is happening here. So when you multiply a matrix with a bunch of columns, then each column of the output matrix can be represented in this manner. Okay, so now this should be familiar to you. So what we saw here is exactly this. So when you multiply k v1, what is happening? When you multiply k with v1, the first row of k gets multiplied with v1, the second row of k gets multiplied with v1, and so on and so forth, right? So what are you actually getting here? You're ending up with the scalar projections of the data points onto your principal components. Okay, so that's what it is. Now I'll finally write down what is the final expression for. I leave this with you. Even though from the exam point of view, this is not terribly important, but it's important to know this. Okay, so I'll leave this with you, and you can think about it a bit more. And if anyone is interested, we can have a detailed discussion later. So this is n cross n, right? So this is our kernel matrix, and v1 dot 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 VR, right? These are what the eigenvectors
Yeah.
Transformed.
of the kernel matrix itself, right? So whatever your algorithm black box is going to return to you, these are unit norm eigenvectors. And lambda 1 to lambda r are your eigenvalues of the kernel matrix again, not any different matrix. So if you multiply these three matrices, okay, this is case. I told you what it is, and this I called it V, right? Capital V. So this I called it capital V, and that is going to be n cross r, right? So you are putting in r column vectors, each of them is of dimension n. The final matrix, I'm calling it D, it's a diagonal matrix. So what will be the dimension of that?
R cross R.
R cross R, right? So that will be just a square matrix with the inverse of the square root of eigenvalues on the diagonals. Okay. So now, if you multiply all this, you will get a matrix which I am calling X prime. So what do you think X prime holds? First of all, what is the dimension of X prime?
N cross R.
N cross R.
N cross R, right? So
Sir, D is that diagonal matrix that we are seeing there, right?
yes. So yeah. So sorry, I'll not call this N cross R. So this product is there. Now I'll make use of this. So this is the final formula which you have to. If you remember this, it's good because it will save you a lot of trouble. So D V transpose K, right? So I'm just transposing this whole thing, right? If you transpose this product, the diagonal matrix comes first, and the transpose of that is just the diagonal matrix. The transpose of this is V transpose, and then the transpose of K is just K, right? Because kernel matrix is symmetric. Okay, so you end up with this. So now, sorry, so what is X prime? The dimensions of X prime?
R cross N.
D is R cross.
R cross N, right? So what do you think this is going to represent? What is this matrix?
That covariance matrix.
Well, not the covariance matrix. So each column corresponds to what?
The principal components corresponding to the transformed features.
Okay, so not exactly the principal components, but the projections of the data points onto the principal components, right? So each column is a data point, or rather each column corresponds to a data point. Okay, and each row corresponds to one feature, right? This is the new feature that you get after projecting the data points onto the principal components, right? So there are new features. You can think about it that way, and so that's what this is. Okay, now you can throw away capital X and use this X prime for some downstream task. Okay, this is what you end up with after running PCA, kernel PCA on the data matrix. Yeah.
Sir, can you explain that how we got that X prime as R cross N and D as R cross R? Means I'm getting till V, but after that I'm not.
Yeah, after that it's a bit tricky. So what I have done is I leave this with you. Okay, I have formatted this as a proper PDF file. I'll upload that. So the same file that I uploaded, I'll re-upload it. You take a look at it and you can ask me again next week, right? Because this is, if I start explaining it, I feel it will take little more time, and I want to go to the demo and maybe get back to this after some time. Okay,
is it because we are transposing V?
Yes, yeah. So we are transposing the whole thing. So in fact, we are transposing the whole thing. See, what we have done is we have expressed this product as this. Okay, so this is what we have done. So we have split this, decomposed this kv1 by root lambda 1 into the product of three matrices, k, the V1s and the diagonal. This is again just matrix multiplication.
And D is that diagonal value which is of means dimension or crosshair.
Yeah.
And R here means number of
No,
features.
D is the entire diagonal matrix only, right?
D is a fully diagonal matrix here.
Full diagonal
Whatever I have
matrix.
not filled are zeros.
Okay.
Okay, so if you now go back to the algorithm, so the algorithm can be more succinctly given as follows, right? So the algorithm is actually very simple if you think about it. So fix K, compute the kernel matrix. I'll make all these capital bold, right? So compute the eigenvectors, and now I'll go back to my convention of not using n here. Okay, so all this remains the same, right? Now what you do is you directly go and form these three matrices. And the matrices are, one is the diagonal matrix, diag of, I'll just call it diag of what? So this is 1 by root lambda 1, and 1 by root lambda r, right? So form this diagonal matrix. This is one matrix you have to form. And then the second one is made up of this V1 dot 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 VR, okay? To form this matrix, we have formed two matrices. Now, the other one you already have, which is the kernel matrix, okay? So if you want to find the projection of your data matrix, the projection of, go down, so the scalar projections, sorry for that. So the scalar projections of the data points onto the principal components in the transform space, right? So we are looking at the transform space, right? So is given by x prime equal to dv transpose k, and this x prime is what we are interested in. Okay, so that's all there is to the algorithm. In terms of the pure description of the algorithm, this is what you need to do.
So this kernel matrix will be given to us, or we have to compute it?
You have to compute, right? If given, depending on what kernel you choose, you have to compute the corresponding kernel matrix.
So we have to choose the kernel itself, like any type of polynomial kernel we have to choose.
Yeah, so you have to choose. There are many kernels, right? So you have to keep choosing. You have to try out different kernels and see which one works best for you.
Okay.
Sir, in a quadratic projection, transforming it, do we lose some information while we're transforming it and projecting the data points?
When we are transforming and projecting,
like we're finding x prime, right, for all the data points, right?
Right.
So do we lose some information about the points, or we don't?
Okay, it's a good question. I think something similar was asked last time also. So let's look at each stage. So when you choose a kernel or when you compute the kernel matrix, you don't necessarily lose any information. But when you if you are going to retain only some principal components here, for example, if this is going to be r cross n, right? So if you choose to retain only 2 cross n, then certainly you are losing information. But are you losing any information even in this stage, right? So, or is it complete? I'm not sure. So it depends on two things, right? What we exactly mean by information is one question, right? So I get what you mean when you say information. So vaguely, I also understand that part, but we have to be a little more precise as to how do we quantify information in this case.
I'm talking about, can I go back to the original data set after
Right, that's good. Yeah, that you cannot do, right? So that's not possible, because sometimes what will happen is the phi itself may not be known to you, right? So for a quadratic kernel or cubic kernel, you can kind of understand what the phi is, right? You can even explicitly construct it. But if you go for something like that Gaussian kernel, which has been discussed, phi is not under your control at all. You don't even know what phi is, right? So going back is not possible. Yeah, in that sense, information is certainly lost.
So phi
Sir, in
in
general,
higher dimensions is like it's not calculated mathematically. There is no mathematical formula for that. It's just computer-driven calculations.
So that's the point of kernel PCA, right? So you don't need to compute phi. So if you notice the algorithm, phi does not appear anywhere in this explicitly. Implicitly, there is a phi. For every k, you do have a phi, but then you don't need to. You don't want to go there.
Mm-hmm. Thank you.
so sir, when we say we are performing kernel PCA in general, then phi will not be calculated. Whatever.
So you may not know phi at all, right? For example, so we have not discussed this kernel so far, but this is if you look at the Gaussian kernel, right? So this is given by e power. So this also we have to discuss. So this is, let me just call it x stands for e. So this is e power norm of x minus y, the whole square by 2 sigma square, right? So this is what is called the Gaussian kernel, right? So the Gaussian kernel actually it transforms, this corresponding transformation is from say RD to some, so this is a different x, it's not the same x. So this stylish x is actually some infinite dimensional space, right? So
Okay.
we don't even know what phi is in this case.
Sir mentioned this type of thing, and he said that this entire thing, that exponential thing, comes from the standard means distribution itself, not a distribution.
Right. So this is something totally hard to wrap our minds around, right? So that's
Yes.
the Gaussian kernel. So Gaussian kernel. So the idea of dot products in kernels, right? Maybe a quick word on that. So the reason these dot products are coming in is because it helps you measure the similarity between two data points. Okay. So the Gaussian kernel, for example, is actually -8. So this is a negative sign. So some quick intuition on the Gaussian kernel, we can actually plot the Gaussian kernel. So it will, but even without plotting, you must be able to understand, right? So when x is close to y, what is the value of k of x comma y?
1.
Okay, right? And when x is very far away from y, meaning when x and y are pointing in, sorry,
infinite
0, it will go to
0. It will go to 0, right? It will go near 0 because this is, what is this actually? This is 1 by e power.
Okay, it's 1 by
right? So, and that something in the something here is actually
then makes sense. Then
yeah.
makes sense.
Okay, so enough of kernels, I believe. Now let's look at some demo. So I'll just walk you through some code that will perhaps give you some intuition as to what is happening in this kernel PCA. Once in a while, I'll show you. I'll also explain what happens in each line of code. So it's not necessary. Okay, so this, I'm installing this so that we can measure the time taken to run different pieces of snippets of code. Okay, so this installs something called auto timer, which will time our code. So that is what it does. And then here what I'm doing is I want my printing to be having only precision of 2, meaning if I print something like 1.2345, I want only 1.23 to come up. Okay, so that's why I'm doing this. So this is just a small.
Sir, you are using random number generator, right?
Yeah, so that will also come up soon. So what we'll now do is we'll quickly write code of PCA. Okay, so I'll just go over this in case someone didn't attend this last time, so we can see how it works. So you pass a data matrix x as input. Okay, that's what PCA takes as input. Now the shape of the matrix is d cross n, and this is how you get it. So d comma n is equal to the shape of the matrix. And what you do now is you mean subtract, right? So x dot mean will give you the mean of the data set along the columns, right? This means get me the means of the columns of the data points, right? So that's what this does. And it's a small thing that you have to do. So this is to convert the mean into a vector. If you don't understand this, it's
minus one here auto determines it, right? Whatever shape.
Sorry?
Minus one is for the auto determination of shape, right?
No. That is for allowing. So it means compute the mean along the columns.
No, that is x is equal to 1. For reshaping, I am saying that minus 1 is for auto determination.
Yeah. So I'm not getting that because that's slightly technical. So let's not get into that. So the covariance matrix, right? Once you have a centered matrix, you can compute covariance matrix. That is XX transpose.
Why have you written x minus equals to?
Okay, that's a shorthand for x equal to x minus. Okay. So the covariance matrix is XX transpose by n. So, and now the black box that I was talking about, right? So that is nothing but the eigenvalue eigenvector computation. So that's called EIGH. Okay, EIGH is for those who have done MLF. H stands for Hermitian. So you have seen Hermitian matrices in MLF. So these are complex matrices where A star equal to A, right? So I hope you remember that. So that is what this EIGH means. For the others, those who have not done MLF, this is just something to get us the eigenvalues and
eigenvector pairs.
These
are in pairs, right? These both are in pairs whenever we do this.
Yes, yeah. Okay, so you'll get eigenvalues and eigenvectors. So I'm going to, so what NumPy does is it returns them in ascending order of eigenvalues. So I need to flip them. I need to flip the whole thing, right? So in fact, I'll just show you the dimension. So eigenvalues, there will be, let's say, d of them. Eigenvectors, there will be d of them, right? So it will give it to you in a d cross d matrix where each column is a eigenvector. So what I do is I reverse the columns. Okay, this is the command to reverse the columns. It is not very important at this stage. All that I'm doing is I'm reversing the columns so that the first column is the first principal component. I'm doing the same for the eigenvalues. And the eigenvalues correspond to what in the case of PCA?
Lambda.
The biggest variation.
Captures the maximum variance.
Yeah, these are the variances, right, of the data along the principal components, right? And I return this pair. I return the variances and the eigenvectors. Okay, so this is what I do now. What we'll now do is we want to measure how much time it takes to run PCA for different values of D. So I have written this down. So here there are, first example has 1000 features, 100 data points, and I'm uniformly generating one data set. You don't need to worry about this part. I'm just randomly generating a data set of size D cross N. And in the second case, I'm generating a data set that has 2000 features. Okay. So this is what it is. So I have to run this, and then I have to run this. Now let's see what happens to PCA on X1. Okay, so it's going to return the whole thing. So let me suppress that output. I'll just show you PCA of X1. So it takes 368 milliseconds. Okay, to run PCA on the first data set. Let's run it on second data set and see how much time it takes. So what is the expectation? Should it take more time or less time?
More time, sir. Cubic of that order of cube.
Correct, right? So it takes 2.33 seconds. So roughly, if you think about it, 2.33 is what? 23 seconds by 0.368 seconds, right? That is the conversion to seconds, I believe. So roughly it takes 6 times more, right? Ideally, it should take 8 times more. So this is what we mean by when we say O of D cube, right? So if you double the number of data points, the time becomes 8 times. Okay, you can run it again. Because of randomness, this will
Generate
keep,
new data.
so it will be different. So if you run it now, it's 323, and if you run it now, it is 2.8. So if you compute this, so it's 2.8 by, it will be slightly higher now. So it will be what? 8 points. So roughly, you see that if you double the size of the data set, the number of features, PCA takes 8 times more time to complete. Okay, so this is what the O of TQ problem, right? So computational cost. So we can fix this. So I'll also show you that code. It's an interesting code. So we'll come down and start from here. So this is, I'll call it modified PCA. So this also accepts the matrix capital X, but what it's going to do is first part remains the same, right? So you're going to get the shape of the data, and you are going to subtract the mean of the data from the data, so that you center it. Now, instead of working with XX transpose, we are going to work with X transpose into X. Okay, we are going to call this matrix capital K. So we do the eigen decomposition, right? So we do np dot lineage dot h, that will give us eigenvalues and eigenvectors of the kernel matrix. Though there is no kernel, there's like it's a vanilla or standard PCA now, but still. So I'm going to call this eigenval eigenvector gain. Okay, and I'm going to revert it. Okay, so now what do we need to do? Once we know the eigenvectors of capital K, what do we need to do?
We need to form the matrix, right?
Sir, you find out the eigenvector and the eigenvalue of K, sir.
That is done, right? So that is what I've done here. So capital K is done.
Yes, sir.
What next? You need to find out the covariance matrix, right? So how do you link this to the covariance matrix?
Phi of X transpose X, phi of X.
Phi is not yet there because we are just dealing with.
Sir, it is the same as the earlier one, sir. Earlier matrix, you had that eigenvalues and eigenvectors will be the same as the here also. Because
so we can multiply.
It is a symmetric matrix and it will be equal, sir.
Okay.
Eigenvalues and eigenvectors will be same, sir.
Right. So
now you can arrive the whatever you want to do now, we can do with this.
Okay, they are not the same, right? Only the eigenvalues are the same, right? So the eigenvectors are different.
Eigenvalues remain same, sir.
Okay. So what you do is you remember that you have to multiply it by X. So X into V1.
Yes.
Okay, so maybe I'll call this capital V so that it becomes easier.
Yes,
and I'm going to do something here which will be slightly non-intuitive, but still. So what will be the dimension of your final eigenvectors for covariance matrix?
Sir, it will be n by n, sir.
And not really, right? So
No,
eigenvectors of the covariance of the covariance matrix.
It will not be n by n into n, sir?
No, right?
D cross
D, sir.
Okay, D cross D, right? If you have D eigenvectors and so they're D cross D. So now I'm going to do something here which is not important now. So there is. I'm going to get the rank of K, so don't worry about this. This will give us the non-zero eigenvalues. Okay, so if you don't get this, it's fine. Now I'm going to store all the eigenvectors of the covariance matrix. Okay, here. Okay, in a matrix called W. So each column will be one eigenvector, and there are such eigenvectors. So that's what W is going to stand for. Okay, so I hope that is fine with you all. So once you have V, how do you get W? So Vi is there. Vi is the ith column of the capital V, and Wi is the eigenvector of the covariance matrix. So I need to go from Vi to Wi. How do I do that?
K times that Vi by lambda I think.
Okay. No, we did this last week, right? So you recall, if you have two matrices, right? X transpose X and XX transpose. You know the eigenvector of X transpose X. How do you get the eigenvector of XX transpose?
It's same
Yeah,
thing, right?
alpha by using alpha, I think.
See, the
N times
eigenvectors
that
and
value.
eigenvalues will be same, right?
No, right? Eigenvectors will not be the same, no? For kernel matrix and the covariance matrix, eigenvectors are different.
So there,
Yeah,
if I
I think
remember right, we multiplied some means n times that uh, value.
Right.
Something
So
like that.
okay. So I request all of you to go back and revise this. So maybe I'll ask this here if it's not clear. So you have a matrix X transpose X, and the eigenvectors are V1 till VR. Okay, and I want to find out the eigenvectors of XX transpose. So what are they?
Because alpha 1 to alpha,
Alpha. Okay, so
and alpha is beta by under root of, I don't
no,
know,
no,
I
no.
guess.
We are not. So so we are using different notation here. So can you?
So xv1 by root lambda 1.
Exactly, right? So
Yeah, yes by under root of.
so that's the one, right? So xv1 by root lambda 1, and so on and so forth, right? So that's what we need to do. So this is what we did, right? Just now, pi of x into v1 by root lambda 1. So alpha 1, whether you call it alpha, beta, it doesn't matter, right? So the best way is to think of it not in terms of alpha, beta as formulas, right? So think about it in terms of concepts, right? You have eigenvectors of X transpose X. You have to pre-multiply that by the matrix X, divide by square root of eigenvalue. That's all you need to do. Okay, so whether I name it alpha, beta, V1 should not matter to you, right? So I hope that is clear. Right. So now if you go back here, now this is what I'm trying to do, right? So what I'll end up with is X into Vi. Okay, so that's what this is, X into Vi divided by square root of the eigenvalue, right? That is exactly the same formula. I just need to put this inside a for loop because I need to do this for every single eigenvector, right? So I'll just put this in a for loop, and I'm basically done. Okay, so I can now return my eigenvalues and my eigenvectors, which are in W. Okay, so that's the way to do it. So I'll, instead of typing it, I'll go back to something that I've
Sir, I
already
think
done.
I'm forgetting something. The way you're doing it, colon and then comma and then I. So is it like from the beginning till I?
Colon, comma, something is, forget about the rows, fix the columns, right? So you're like,
Okay.
I want a particular column, therefore that's why the second index corresponds to the column. Okay, so I'll go back to what I have already written. So there's a lot of code here, so don't be confused by that. So if you now run it on x1, right? So x1, this modified PCA takes 34 milliseconds. X2 it takes 73, right? You see it's comparable. Earlier it was taking a lot more time for X2, right? So X1, X2, the difference was, this was 8 milliseconds and this was 330 milliseconds, but and this was 4 seconds, right? Now with the modified one, PCA X1 takes 742 milliseconds. Sorry, PCA X1 takes 34 milliseconds. This takes 73. So that's the benefit of going from X transpose to X transpose X. All right, so this is one idea. So the other one is, I'll just show you so I've written kernel PCA. So maybe I'll share this collab. You can experiment with this. So example 0 is not great, but example 1 is like this, right? So you have a bunch of data points like this, so which are coming from some circular region. So you have two data points, two classes of data points, the green and red ones, and you run kernel PCA on it. Okay, you run kernel PCA with P is standing for polynomial degree. So it's a polynomial kernel. And what I'm doing is I'm only retaining the top two principal components.
Sir, what is sigma there?
Sigma is for the Gaussian kernel, but
Okay.
for now, let's just look at the polynomial kernel. So if you project it, you end up with something very similar, right? So if you change P, you'll notice that we change P and show you what happens.
The kernel PCA function is defined by you or is a predefined program?
No, I have defined it actually. So I have written it down here. It's the same thing that we discussed now, right? So you compute the kernel matrix here, and then you get the eigenvalues, eigenvectors. You form the matrix capital V, capital D, and then dV transpose K. Whatever we discussed, the same thing. I've just written it as code here.
Can you share this in the chat, or where can we access this?
I'll be uploading this in that notes folder. Okay, so if you change P, right, you'll notice that depending on what your kernel is, you'll get different kinds of representations. So it's taking some time. So let's now run this. Okay, I don't add anything. So let's say I give a polynomial of degree 5, right? You see that the representation changes a bit. Now can, and you also should notice that this number here represents the proportion of variance captured, right? So I'm retaining top two components. So that's like lambda 1 plus lambda 2 by sigma lambda I, right? So that is 61%. Now if I go to 10, you will see something else happening. So all the red points here get truncated into a very small region and the green points are surrounding it, right? So in this particular example, there's no advantage in doing kernel PCA and retaining the top two PCs because nothing important is happening, okay? No change in a sense. There's one more example that slightly better. So if you look at it, this is another data set, okay? Now, if you look at kernel PCA with polynomial kernel, you end up with this kind of a representation. All right, so can anyone see what has happened here? So this is the input data set. And if you do kernel PCA and retain the top two principal components and project the data onto that, you get this.
So it has been like folded into one quadrant.
Right. So what would be the advantage of something like this happening?
So symmetric property.
Okay, from a machine learning standpoint, right? So you're trying to extract insights from data. So think about this as, so this is what we call a classification problem, right? So I want to differentiate between green points and the red points. And let's say I want to differentiate the 2 points using just a line. So if I can draw a line in this region and say that all the points that fall on one side are red and all that fall on other side are green, that will be great. Okay, so if I can do that, it will be great. Now, does kernel PCA allow me to do that? It allows you to do that, right? So if you think about it.
So I kind of missed what you said in the last 30 seconds.
Sorry, yeah. So see, this is what we call a classification problem, right? Meaning you have to differentiate between the red points and the green points. So you have to somehow separate the red from the green points. So it will be convenient if we can do it with a line. So this is what is called a linear separator. So can we do it using a line here in this setup?
Oh, sir,
No.
non-linear shape will be required.
Yeah, so you can't do it with a line. So something non-linear will be required. But if you do kernel PCA and reduce it to 2 dimensions, you end up with this kind of a setup where the line is possible, right? So you can actually draw a line, say at -100, horizontal line, and that will allow you to separate these two data blocks, right? So this is what is called a downstream task, right? So the prof has been referring to a downstream task in his lectures, right? So this is a typical downstream task where you want to, let's say, learn a classifier. So learn a line that separates two different classes of data points, and you can't do it here. And kernel PCA allows you to kind of linearize the whole thing and draw a line to separate the 2 points, 2 classes of points.
So here the function would be like xy minus 1, right?
So we have used a polynomial kernel. So the actual function that is used to plot this is called an asteroid. Or I don't know exactly what it's called. So it's asteroid curve. Yeah, that's what it's called. So it's some complex curve. So anyway, I'll share this with you. But by using a suitable kernel, you are able to linearize this. Okay. So that is one example. The third one is if you have, so this is another example, right, where your data points are in R3. So there is a sphere. You can think of one ball inside another ball, and data points are situated on the surface of these 2 balls. So the green points are on a bigger ball and red points are on a smaller ball. Okay, same number of points. Now once again you run kernel PCA, but this time instead of a polynomial kernel, you use a Gaussian kernel that we just saw with that parameter sigma as 40, and you end up separating the 2 classes neatly this way. Okay, so this is an example of using Gaussian kernel. Okay, so this is these are couple of scenarios where you can use PCA. So one point I have to mention, see, the linearization happens only in the higher dimensional space. Okay, so it only happens in R capital D, R superscript capital D. So that's where the linearization happens. It doesn't happen in the original input space. Okay, but what we are doing is by choosing these parameters carefully, we are able to get a kind of a nice separation between these 2 classes of points. But the actual linearization that we are talking about is happening only in R6 or whatever, right? Higher dimensional space.
Sir, by linearization, you mean fitting a line to separate?
The linearization, I mean the data set lies in a linear subspace, right? That's the assumption. So in a higher dimensional space, if you transform these points to a higher dimensional space, they will all lie in a linear subspace in that higher dimensional space.
Okay.
Okay, and it so happens that when you project them onto the first 2 principal components, you are able to neatly separate them using a line. So this is a different kind of separation. Here also linearity is involved, but it's of a different nature.
Okay.
Sir, so this is what you're talking about, the separation in or representation in linear form in a higher dimensional space, and this thing which we are getting using the kernel PCA, using some things. So, are these two things different?
Yeah, these two are different because see, when we say transformation makes the data linear, that is in some higher dimensional space. Okay, that is what I mean by linearizing the data. Okay, that is something different. Now, what I've displayed here is when you project the data onto your principal components, and if you visualize them, they are separable using a line. Okay, and that's a useful thing to have. So you can draw a line to separate these two blocks. That's a useful thing to have. Now, this is a different linearity that I'm talking about. Okay, so that's all I had. So any other questions from this week? We can discuss them. If not, we can close. Are there any questions?
Sir, I was doing activity question, and in the third activity question, there we need to find the means the kernels or the d-dimensional values, which when taking the dot product we get zero. So how to do those type of questions? Because sir hadn't given any example for that.
So if you take kernel, it will bring you 0 if the dot product is -1, right?
Hmm.
Yeah, so
And
you have to,
hmm.
that's what
Do
you have
you
to look
have
for.
access? Do you have access right now to the portal?
I do, but I believe what you're asking is if you want the kernel to be 0, right?
Basically, it says that consider data points xi 1 to n, and there is some function which is given by f1 minus a whole square plus f2 minus b whole square is equal to r square. And then consider a point which is in some 6-dimensional space, and then you have to, which of the following transformation phi will result in phi xi transpose u is equal to 0 for all I.
Okay. So yeah, so this is the equation of a circle, right? What we just saw. So
I am confused about this because in the lecture just previous to this, sir actually did something which was not means I was not getting what he is doing. He was transforming the space, but how he was doing it, I was not able. Was it arbitrary, or actually he calculated that particular thing? So that is the thing that I want to know.
okay, that comes from this kernel matrix, right? So if you have a quadratic kernel in terms of x and y,
Mm-hmm.
so this is so x1, x2, and you have y1, y2.
Hmm.
Okay, so this is quadratic kernel, right? So this is x1, y1 plus x2, y2 plus 1 whole square.
Hmm.
And then you just expand this. So you will get x1 square, so x1 square, y1 square plus x2 square, y2 square
Mm-hmm.
plus
Okay.
1, all that, right? So,
Hmm.
and then you'll have, so if you want to go the distance, it's 2x1 y1 plus 2x2 y2
Sir,
plus,
sir, can I share my screen? I just want to understand this, which I understood. This thing I understood, but
ah,
sir actually did something which I want to show you. Means, is it
ah,
the same thing that you are saying?
yeah, so it's the same thing. Yeah, so I'll come to that. So what you would have done is you would have now, so he's basically writing this as root 2, that you're looking at the root 2 x1, root 2 x2.
No, sir. Actually, he was taking F1, F2 in R2, and then he is transforming it to R6. But how he is transforming? Does he taking? Is he taking things arbitrary or
No,
using the?
no, yeah, that's what I'm coming to, right? So this
Hmm.
is, he's not arbitrarily doing it. So you you see a dot product that is coming here, right? So you can extract a dot product from this. That is, so if you do phi of x is same x1 x2. So this is nothing but, so you have an x1 square, therefore I want an x1 square here. So and you want a y1, so you want x2 square also. So I want x2 square here, and I want a 1, so I have a 1 anyway. And I want x1 and y1, so that, which means I need x1 here, and since I want 2x1 y1, I need root 2 x1 on one side, and I want likewise root 2 x2 on the other side, so that I get this term, and I want root 2 x1 x2 so that I get the last term. So this is the way to, this is what you would have done. So this is R2 to R6.
He was doing it on the basis of F1, F2.
That's the same thing, right? It's x1, x2, F1, F2.
He said like U belonging to A square plus B square minus R square 1, 1, 0 minus 2A minus 2B. Something like that.
So that's the circle, right? So if you have points on a circle, then let's say the equation of the circle would be something like x1 minus a whole square plus x2 minus
b whole square is equal to R. Yeah.
So it will be something like this, right? So which means the circle, this will satisfy the equation x1 square plus 2ax1, minus 2ax1.
Okay, we are expanding that. Okay.
Yeah, so you get plus x2 square minus 2bx2 plus b square. So plus a square plus b square minus r square, right? So now this can be written in terms of a dot product with some w times phi of x1 x2. So if you just need to keep this side by side so that you know what is happening. So I am coming up with a similar matrix on this side. So what should the dot product be? So x1 square is 1, so I just need to dot it with 1, and x2 square also there is just 1, so I need to dot it with 1, and instead of 1 I need a square plus b square minus r square, and for root 2 x1 I need 2a, so I need 2a root 2, right? So no, a root 2. No, so minus 2a x1 I need finally, so I need to get rid of the root 2 somehow. So
yes,
I just divide by root 2 and minus 2a, so that will give me minus, so if you multiply you will get 2a x1, right? Minus 2a x1, and similarly you need this, so you need minus 2b x2 here, right? So this will be minus 2b x2, and there is no x1 x2 term, so you can just make this 0. So the w that you want is this. So this w transpose phi of x equal to 0 for all the points that lie on the circle.
Sir, this 1, 1 that you took from the very beginning, that 1, 1 means how we are computing that?
Because there is only one, the coefficient of x1 square is 1.
Okay, so you are taking actually the coefficients and calculating them for w.
Yeah, because I need w transpose phi of x to be 0, right? So yeah, so I don't know what he said exactly, but is he saying w transpose phi of x equal to 0 at the end?
He was not using this. It would be better if I can show you. Means I understood that what you did, and I understood that he's actually calculating the coefficient. But if I could share, maybe things will become clear to you.
Once again, it's a slide, right? It's in the slide, means I have the slide with me. So
yes, then you can go to the third lecture 2.3, and there is a slide where F1, F2 changes to 1 f2 1 f2 2 f1 f2 f1 or f2, and before that there is some function which is actually being calculated. I think you also calculated the same
Yeah,
thing.
yeah. So it's the same thing. So he has written phi of x transpose u equal to 0. I have written w equal to 0. That's the only change, right? So
but means he is using minus 2a and minus 2b.
yeah, that's
So
because he's using a different feature. So he's not using a kernel, right? So he's not going via the kernel. He's using x1, x2 itself. He's
yes,
using
yes.
f1, f2 itself. That's why.
So we are getting that from the original function that he calculated as star he marked.
Yeah. So
f1 square a square minus 2 f1a, something like that.
that is the equation of the circle expanded, right? So he's just
Yes.
expanding the equation. He's just expanding this one. Instead of x1, he's using f1 and
Okay, then he is actually calculating the coefficient. I thought that he is directly calculating, means the values. You're putting the values and calculating. Okay, I got it. So he is actually calculating the coefficient there.
yeah.
Okay, so and similarly we have to do for that question that I asked you.
So how are we getting root 2 here?
That's because of this kernel, right? So if you go
Kernel.
via the quadratic kernel, then the phi corresponding to the quadratic kernel needs a root 2 so that phi of x transpose phi of y will have 2 here. So we have 2's here. So if you take dot product, the root 2 and root 2 will combine to give a 2.
Okay.
Okay.
Yes, yes. So we will do the same thing for our question that I asked.
Which question?
Consider the data point and we have to means basically find phi of xi transpose u is equal to 0. Same thing that you did, right? We will do
Yeah,
this.
yeah, yeah.
Okay. So
Okay, any other questions in this PCA, kernel PCA? If not, we can wind up.
Okay, sir.
Okay. Yeah, so then we'll stop here. See, it has been hard this week. I kind of understand this, that PCA and kernel PCA especially can be hard, but just stick to it and go over the lectures once more. So that's the only suggestion I can give.
sir, from the exam point of view, what are the aspects that we need to take care of in this kernel PCA thing? Knowing the algorithm is one thing, I understood, but after that,
So that I don't really know. So yeah, everything surrounding the algorithm you must know.
those dimension that you and the calculation of whatever you sort, right?
Yeah, the whole thing is required. Okay, we'll meet again. So Monday, a different instructor will be taking the session. So I'll come back on Friday. So we'll share now the sessions between us. Okay. So thanks for joining. We'll meet again.
I have one question left. I think I forgot to ask.
Yeah.
Is it the right time to ask, or should
Yeah,
I?
yeah.
Okay. So for 2.3, question number 2, 2.3 activity question 2.3.
Okay. What is the question?
So I'm pasting that in the chat.
Yeah.
It's fully accepting. It's not coming in a proper format. So
Same time.
there is a data format. So there are data points which are indexed from I to n, and they are lying on a circle f1 minus a whole square, like the formula of the circle, where a, b, and r are integers. So what they are actually asking is consider a point u which looks like this.
What is the
Okay, yeah.
question number?
I think I
So-
have mentioned that 2.3, question number 2. So it's like so the points are, the first point is a square plus b square minus r square, and that's the first point. The rest of the points are 1, 1, 0, and minus 2a and minus 2b. So they are actually asking phi xi transpose u. What will, like, which of the following transformations will result in phi xi transpose u equal to 0?
Okay, so we discussed this just now, right? So we didn't discuss it for the exact phi, but you can come up with the transformation, right? So if you want to do that particular transformation, you can just have x1, x2 here, and so you can remove this part, and you just need to compute the corresponding dot product. So what w or what u will give you that required dot product? So it will be x1
So for
square.
example, sorry for interrupting. The thing is, a square plus b square minus r square will be there in the first place. So the coefficients which are coming out of the variables which are coming out of that will be 1 for a square plus b square minus r square, if I'm getting it correct.
Yes.
So wherever the scalar value 1 here is, that corresponding value coefficient here will be a square plus b square minus r square.
Got it. I think I'm able to understand now that.
Yeah. So
Yeah. Thank you.
yeah. Any other questions? If not, we'll.
So again, the list of questions, if we have sample questions, like 1 or 2 questions, numerical questions which are based on the derivations which we have done. Are there any questions which are there? Referral questions.
You can find them in the previous year question papers, so they will have quite a few of them.
Okay.
So there is this acegrade.in, right? So which is
Yeah, which solutions I was asking basically.
okay. So that I am not sure if we have with solutions, but
Okay. No worries.
all right. Yeah. So thanks for joining. We'll meet again next week.
Thank you, sir.
Thank you, sir.